Hi, I'm Wissam Sab from MCAD Engineering, and after the design of the power amplifier presented by Chris from AWR, we will present here a solution to extract an equivalent behavior model of this power amplifier to allow a precise design of a complex RF system. There are two different types of users who need behavior models. Circuit designers usually look for an equivalent model when they want to show the performance of their circuits to their own customers. On the one hand, in order to protect their intellectual property, circuit designers generally look for a type of black box model that does not reveal any design secrets. On the other hand, they want to make sure that the behavior model will be very accurate, even in non-perfectly matched conditions or in nonlinear conditions. Other users of the model are the system designers. Their desire is to evaluate the impact of circuit performance on the entire communication system to ensure that the system will provide adequate performance before production. Indeed, testing a system with hundreds of thousands of circuits can be very expensive in time and money, as in MIMO systems, which require costly and time-consuming measurement processes. The aim in this case is to replace this validation work with a very reliable simulation work. Extracting a true circuit behavioral model is not so simple, as multiple parasitic effects will occur in the circuit. In addition to the nonlinear behavior and the influence of the load, which can modify the performances of the circuit, if the RF or microwave signals are modulated, they can be distorted by a certain memory effect, which modify the instantaneous response of the PA as a function of the previous operating condition. There are mainly two types of memories: short-term memories, which depends mainly on the response of the corresponding circuit in the high-frequency bandwidth, and the long-term memory, which is related to a low-frequency phenomenon, such as low-frequency intermodulation products that will not be feedflowed by the bias circuit, or thermal effects driven by the envelope modulation. In addition, these two memories may have a kind of mutual coupling, which must also be integrated into the behavior model. After this brief introduction, let's see how to extract a behavior model, then how to validate such a model in order to run a system simulation in a third-party system simulator, such as Visual System Simulator from AWR. At the very beginning of the proposed design flow, to extract an equivalent circuit model, we need to know the behavior of the circuit. The input data must be provided by a circuit simulation based on the use of our compact transistor model or from some measurements taken with a dedicated vision control test bench. This input data will then be read by our vision circuit modeler, which will provide an equivalent behavior model. Several models can be assembled to create a robust and efficient macro model if necessary. Finally, this model can be exported to a third-party system simulator to ensure that the overall performances of the system complies with the target specification, which will ensure a perfect control of the bottom-up design flow to avoid further system optimization or modification once the production is launched. To facilitate this work, if the initial data is provided by circuit simulation, MCAD created simulation templates to generate the input file describing the behavior of the circuit. To capture the nonlinear behavior of the PA, for example, an AM/EM and AM/PM harmonic balance simulation will be launched. We can see here the spread of these curves as a function of the carrier frequency, highlighting certain high-frequency memory effects. Once we have this input data, we will use the circuit modeling toolbox. This one provides dedicated templates depending on the kind of circuits to be modeled, as it could be power amplifier, but also limiters, multifunction chips, LNAs, mixers, or even passive circuits such as bandpass filters. In this latter case, S parameters files will be used to extract an equivalent model of this passive circuit to enable time domain simulation. Indeed, system simulators are used often for data flow simulation. Note that our modeling toolbox can also provide equivalent model of the multifunction chips, which is quite useful to model RF circuits such as phase shifter or digitally controlled gain blocks. For a given circuit, we will select the most relevant model depending on the observed behavior. Indeed, no need to choose a very complex model if the behavior of the circuit is simple. This will complicate the simulation of the system without any benefit. So, depending on the phenomenon observed, we will select a model that will integrate a unilateral or bilateral behavior with possibly high or low frequency effect, or even the influence of the temperature. Once we have selected the model of interest, we will define the path of the file containing the input data, and we will adjust the parameters controlling the nonlinear order of the model description and the fit against the frequency. The modeling work usually begins with a low-order description, which is increased until we reach an acceptable error between the model response and the original data. It is quite simple to see the influence of these parameters because the extraction time is very short and the user interface makes it easy to visualize the results of the simulation. A test plan can also be used to test the model under different operating conditions with different stimuli. Here is an example. We can observe here that the model is in perfect agreement with the initial data as the function of the power and frequency. As part of the design process we are proposing to this workshop, you can see the fit we were able to obtain on the power amplifier designed by Malcolm in the previous presentation. Again, the simulated RF performance with microwave office and the performance achieved with vision are perfectly aligned in magnitude and phase. In the next slides, we will see how to go further in validating the model, examining in particular some key figure of merits when using modulated signals. By performing a simulation of our power amplifier using microwave office with a two-tone signal, a variation in performance is observed when the tone spacing is swept. This is visible on the left graph because the overall gain shows a dependence on the two-tone spacing, but the dependence is even more visible on the right graph because a clear resonance of performance is visible for 30 MHz tone spacing. Resonance also has an impact on the third-order intermodulation products that can be simulated at different power levels. On the left side, the low-frequency memory, mainly caused by the bias circuit, will create a strong nonlinearity for 30 MHz tone spacing. On the right side, one can also see very low-frequency memory effects, rather caused by the thermal effects and trapping that occur in the transistor. This parasitic phenomenon simulated because our transistor compact model integrates both traps and thermal circuits. Once the behavior model of the circuit is extracted and validated, the schematic editor can be used to connect different circuits together. In this way, a subsystem architecture can be represented. With the source and probe palette, we can perform a quick assessment of the overall performance to ensure, for example, that the subsystem architecture is well done to meet target specification. Once this work is done, it is possible to check system performance using realistic modulated signal. Here are the performances of the amplifier designed with microwave office, as well as the behavior model simulated in vision. The same variation of nonlinearities with a two-tone spacing sweep can be observed around 30 MHz. So in this case, it was mandatory to use a model with both low and high frequency memory effect behavior. More than the performances obtained with a two-tone signal, here are the results of the simulation with a multi-tone modulated signal. The spectral regrowth of the ACPR, depending on the power level, show a realistic behavior of the model. Vision also offers the control of test benches with vector transceivers, spectral analyzer to verify the model accuracy with this type of stimulus. Once the model is validated and qualified, it can be exported to a third-party simulator such as VSS. Model export is more than just an export. The export feature allows you to export a simple circuit model or a subsystem macro model if multiple circuits have been concatenated together. In addition, this model integrates its own equation solver in the third-party simulator to process time domain data flow simulation to ensure that the calculation of the modulation distortion caused by the various parasitic effects will be managed effectively, such as memory, temperature variation, or internal impedance mismatch inside the circuit. Once the macro model is exported, a system simulation can be started with a high level of confidence for the results obtained. To demonstrate the superior capabilities of our models, we recently launched an ongoing research activity with a simulation of an active antenna system used to do beamforming, as is currently required to design 5G MIMO systems. We have been able to demonstrate that the beam steering simulation is very different when using unilateral model and bilateral models. This is explained by the fact that the steering will significantly influence the matching of each amplifier, modifying in return the power supplied to the antenna by each branch. For illustrative purposes, because of the mutual coupling between each patch of the antenna, here is an overview of the active load pull effect on each PA as a function of the phase difference between each branch. We can observe that this coupling can have a significant influence on the output power provided by each PA and can then significantly modify the antenna emission diagram. This work will be continued for other presentations. Thank you very much for your attention, and come see us at our booth on the show floor to learn more about vision. Thank you so much.